Hey everyone, welcome back to the channel Code with AKJ. Today is day 47 of solving LeetCode 75 challenge, and today's problem is nearest exit from entrance in maze, that is from graph BFS section. So if you are enjoying this series, make sure to hit that subscribe button and turn on the notification bell for daily DSA problem, dry run and time and space complexity analysis. So let's quickly get started with our problem statement. So the problem statement says you are given a m cross n matrix maze, zero indexed with empty cells represented as dot and walls represented as plus. So you are also given the entrance of the maze, where entrance is in the form of two indices, that is entrance row, entrance column, denotes the row and column of the cell you are initially standing at. So in one step you can move one cell up, down, left or right. You cannot step into a cell with a wall, and you cannot step outside the maze. Your goal is to find the nearest exit from the entrance. An exit is defined as an empty cell that is at the border of the maze. The entrance does not count as an exit. So return the number of steps in the shortest path from the entrance to the nearest exit, or -1 if no such path exists. So we are given a 2D matrix representing a maze. So here dot means an open path and plus means a wall. And you can move up, down, left or right. And you're also given the entrance coordinate, and your task is to find the shortest number of steps to reach the nearest exit, which is an open cell on the boundary, that is edges of the matrix, and excluding the entrance itself. And finally, if no exit can be reached, then we need to return -1. So we can understand this given problem statement with the help of this given example. So this girl is at the entrance. From this entrance point, we need to find the number of steps in the shortest path, that is from the entrance to the nearest exit. We cannot move to this particular cell. This is not considered as an exit, because the only direction we'll move are up, down, left or right, not diagonally. So for this given example, we have only two exits and we need to find the minimum number of steps. So for this given exit, we'll just need one step, and for this given exit, we need two steps. So the minimum number of steps required here is 1. So for this given example, our answer would be 1. So coming to the second example, this is the entrance coordinate. We have only one exit in this given example, and the number of steps required to reach that particular exit would be 2. That is from here to here and from here to here. So for this given example, our answer would be 2. Coming to the third example, answer would be -1, because we cannot consider the entrance coordinate as an exit. So there's only one more cell other than the entrance, that is a wall. So we cannot move in any of the directions. So we'll directly return -1 in this case. So that is all about the problem statement. So let's quickly go through our brute force approach, and then we'll move on to the optimized solution. So let's first think brute force approach. So we'll try DFS from the entrance. So here circle represents the entrance, the plus represents the wall, and the dot represents an open space. So we'll try to use a DFS from the entrance, and we'll explore all the paths recursively, and then we'll track the minimum steps required to any boundary cells. So let's quickly go through the steps here. So since we are using DFS, we'll give a DFS call, sending the entrance coordinates, maze matrix, the minimum number of steps, which would be initially the largest value. So let's consider the steps initially would be int max entrance vector. So we'll start from this particular entrance coordinate. We'll send the index value of this given entrance coordinate, that is x value and y value. And from this coordinate, we'll try to explore all the possible paths in all the 4 directions. So we'll also have the 2 vector, which will store the values of rows and which will also store the values of y. So based on the 4 directions, we'll have the values here, both in row wise and column wise, and we'll explore all the 4 directions with the help of this DFS function. So from this given entrance coordinate, we'll try to explore all the 4 directions, and until or unless we reach an exit, we'll try to explore. For a recursive call, if we didn't find an exit, we'll try to backtrack from that cell, and we'll try to reassign the value to that particular cell. So while visiting to a particular cell in a particular direction, we'll try to mark it as visited, and if finally we have found an exit, we'll calculate the minimum number of steps, return. And if suppose we didn't found an exit for a recursive call, for example this particular direction, so the number of cells which we have visited throughout the path, try to backtrack and again mark it as unvisited. So that would be the step. So generally this DFS approach explores all the paths in all the four directions, and it may revisit the same cell many times in different paths, and we are using backtracking to unmark the visited cells after each call. These are the steps for our brute force approach. So the time complexity and space complexity of our brute force approach here would be, since we are trying a DFS function in all the four directions, so each call takes m cross n time complexity, and since we are taking in all the four possible paths, so the total time complexity would be 4 cross m cross n in the worst case due to exponential branching. And the space complexity here would be O of m cross n because of the recursive stack, as we are visiting each and every cell inside our maze. This would be our brute force approach, where we are using DFS approach and trying to explore all the visible paths in all the four directions, which ultimately becomes exponential. Hence, the time complexity will be 4 cross m cross n, and space complexity will be O of m cross n. So let's quickly look at the code and let's move on to our optimized approach. So here's the code for our brute force approach. I have declared minimum steps, which would be a larger value initially. So I have initialized with int max. I've also declared the m and n values, which are the size of row and column of this given particular maze. And I've also declared the directions 2D vector globally, which we can access in any of the functions. So our main function starts with this, and we'll store the row size and column size in both the variables m and n. We'll also use a visited 2D vector, which would be initially false for each and every cell, which means each and every cell initially is marked as unvisited. And now we'll give a DFS function call, sending the entrance coordinate is entrance of 0 and entrance of 1. We'll also send the maze matrix entrance vector and visited 2D vector and 0, which is the minimum steps initially. DFS function goes like this. We'll have two base cases. One case would be if the given coordinate is out of bound or a wall, or we have found a visited cell, we'll directly return. And second base case here would be that if the current cell is an exit, that is this particular cell in this given example, we'll track the minimum steps by comparing it with our current steps value using minimum function, and we'll return. So these are the two base cases for our DFS function. So our first step in our DFS function would be to mark the current cell as visited, and second step here would be that for all the directions we'll calculate our new coordinate, that is the current coordinate plus direction of 0, the current y coordinate plus direction of 1, and then we'll again give a DFS function call with the updated coordinates, increasing the number of steps here. So the steps here would be steps plus 1. So again there will be a new function call, and we'll again check with our both the cases, and if it does not satisfy any of the cases, we'll again mark that particular cell as visited, and again from that particular cell we'll again explore all the four directions. So in this way, until or unless it reaches any of the base case, we'll try to explore all the four directions. And if we didn't found our exit, backtrack from that particular cell, and while backtracking we'll mark the coordinate as unvisited by making the visited of x of y as false. So in this way, with the help of our backtracking and DFS recursive call, we'll explore all the possible paths in all the possible directions. So this would be our brute force approach. So let's quickly run this code. It's working, so let's submit. As you can see, it gives us time limit exceeded, as the time complexity of this approach is O of 4 cross m cross n, which is highly inefficient for larger inputs. So we'll try to optimize this approach and bring down our time complexity. So as we have seen in our brute force approach, it gave time limit exceeded, as the time complexity of that particular approach was exponential almost. So why the DFS approach didn't work? Because it generally explores deep, not wider. So from this cell it goes to this particular cell, and from this cell it goes this particular cell, and then it will check for the base condition, and if it does not satisfy that particular base condition, it again gets called back, and from that particular cell again we'll have a different function call to another direction. So it goes deeper and deeper, and finally when it reaches any of the base condition, either it is true or false, it will again get back to the previous cell, to the initial cell. And since we are using this particular step in all the four directions, our time complexity becomes 4 cross m cross n. So this means it might explore long paths before finding the shorter exit. So for this given example, this path is the shortest path. And also we have to mark visited and backtrack to explore all the other options in all the 4 directions. So brute force via DFS is inefficient for shortest path problem, which is obviously not optimal. So to find the shortest path in an unweighted grid, the best choice is breadth first search. Why? Because BFS explores layer by layer. So let's consider the same example. So BFS approach, it goes layer by layer, that is level order traversal. So if you start from this given cell, it will check this cell as well as this cell. Generally uses queue based approach. It will push these two cells inside our queue. Again for these cells, it again checks its neighbor values. So in this way, the first exit we find is guaranteed to be the nearest. So in this example, the nearest exit here, when we consider this particular neighbor, is the smallest and the first exit. So the first exit here we have found is the nearest one. So BFS approach confirms that the first exit we have reached would be the shortest one. So let's go through every step of this given approach and understand how this BFS approach gives us an accurate solution in less time complexity. First step here would be to use a queue to perform level order traversal. So we'll use a queue. The second step here would be to push the entrance cell inside our queue. So we'll have entrance of O and entrance of 1 here. And the third step here would be that we'll track number of steps taken at each level. So initially steps would be 0, and for each and every level, that is for each and every neighbors of a current cell, we'll increment our steps by 1. And for each cell here, we'll explore all the 4 neighbors, that is up, down, left and right. And if a neighbor is within our bounds, that is it is within our maze bounds, that is x is greater than equal to 0, y is greater than equal to 0, x is less than r minus 1 and y is less than c minus 1. So if it is inside these bounds and it is not a wall, that is it is not a plus character, then we'll mark that particular neighbor as visited and we'll push that coordinate inside our queue for further processing. So that would be our fifth step, and the final step here would be that the first time we reach a boundary cell, that is we'll have a condition that if that particular current cell or the current neighbor is an exit, then we'll return the number of steps. As the BFS approach, it ensures that the first time we reach a boundary cell that is not the entrance is the shortest path exit. So let's quickly dry run with the 2 examples and let's quickly code that approach. So here I have drawn the first example. So let's quickly dry run our BFS approach. So the first step here would be to take a queue and push the entrance coordinates. So here the entrance coordinate would be 1, 2. We'll mark this particular current entrance coordinate as visited. So we'll mark this with plus sign, which means we have visited this cell. So initially our steps count would be 0. And we'll have a directions vector which will store all the coordinates of xy in 4 directions. And now we'll start processing our coordinates. So we'll use a while loop until unless the queue becomes empty. Grab the size of our queue. So here size would be 1 and we'll increment our step count. We have started processing our first coordinate. So until or unless this size becomes 0, we'll first pop this current coordinate. So our current coordinate would be x value 1 and y value 2. We'll navigate to all the 4 possible directions with the help of our direction vector. So we'll use for each loop for 4 directions and we'll calculate the new neighbor. So let's first write the direction values. So it would be minus 1, 0, 1, 0, 0, minus 1 and 0, 1. So our new x would become 1 plus minus 1, that is 0, and new y becomes 2 plus 0, 2. And here we'll first check whether it is inside the bounds of our maze or not. So we'll check with the help of a condition that is new x is greater than equal to 0, new y is greater than equal to 0, new x is less than m, new y is less than n, as well as the maze of new x and new y is not a wall. Since this neighbor field is not a wall, we'll consider this as a valid neighbor, move inside our if loop. So all these conditions would be inside our if condition. So if it is inside our bounds, we'll enter the if loop, and first we'll check whether this given cell is an exit or not. So to find whether this given cell is an exit or not, we'll again have few conditions, that is new x should be 0, or new y should be 0, or new x should be r minus 1, or new y should be c minus 1, which means first row or the first column, or the last row or the last column. So these condition make sure that the given cell is at the boundary cell or not. So if it is, then we can say that we have found our first exit and will return the number of steps. If not, we'll mark the current cell as visited and will push that particular cell inside our queue. So since this given cell is an exit cell, we can confirm that we have found our exit and the step here was 1. So we'll directly return 1 in this case. So for this given example, our answer is 1. So this was a simple dry run for this given example 1. So let's try to dry run another example, example 2, and then we'll code this given approach. So let's do a dry run for this given example 2. So the first step here would be to take Q and push the entrance coordinates. So here the coordinates are 0, 1, 2 and 0, 1, 2. So the coordinate of our entrance cell would be 1, 0. So we have finished our second step. Third step here is to initialize our step value with 0. Mark our current cell as visited, which means we'll set this as a wall, as we don't need to consider this cell as an exit. We'll have a directions vector in all the 4 directions along with its x and y coordinates, and we'll process this queue until or unless this queue becomes empty. We'll grab the size first, and until or unless this size becomes 0, we'll follow few steps. So since we are started processing with our first coordinate, we'll increment our step from 0 to 1. So the current x value is 1, current y value is 0, and with the help of our direction vector, we'll calculate our new x and new y. So here our new x and new y would be based on our first direction minus 1, 0. Our new x would be 0 and new y would be 0, which is the upward direction. So after calculating our new x and new y coordinate, we'll first check whether it is present in our bounds or not. It should be an open space. So since 0, 0 is inside our bounds, but since this is a wall, we'll neglect this neighbor and we'll continue with our next direction value. So our next direction value based on our directions vector would be 1, 0. So our new x would be 2, new y would be 0. So 2y becomes the downward direction. So again, this particular cell is inside our maze bounds, but it is a wall. So we cannot move in this direction. So we'll neglect this cell as well. So we'll again calculate our new x and new y value based on our directions vector. So next direction would be 0, minus 1. So new x becomes 1 and new y becomes minus 1, which means the leftmost cell of this current cell. So since it is out of bound, we'll neglect this direction as well. So the only direction we have left is the right direction, the cell which is present at the right direction of this current entrance cell. So the next new x would become 1 and new y becomes 1. So since 1, 1 is inside our bound of our maze and it is an open space, so we'll consider this cell as a valid cell and we'll mark it as true. So we'll first mark it as true and we'll push this cell coordinates inside our queue. So since we have popped this index in our first process, our new index inside our queue will be 1, 1. So this would be our first iteration for a current entrance cell. For the second iteration, we'll pop this current index, we'll increment our step from 1 to 2, and again we'll check all the neighbors of this current cell with the help of our directions vector. So again we'll move upward direction. Since it is a wall, we cannot move. the left direction, since it is a wall, we cannot move in this direction. If we go downward direction, since it is a wall, we cannot move in downward direction. The only direction we have left is the right direction, which is an open space, and it is inside our bound of our maze. We'll consider this cell as a valid cell. We'll first mark it as true by filling it as a plus character. So before pushing that current index value inside our queue, we'll also have a check whether the current cell is an exit or not. So when we consider this cell, since it is present at the boundary of our maze, it is considered as an exit of our maze. So we'll stop our iteration and we'll return the number of steps here. So since the number of steps here is 2, so we'll return answer 2 for this given example. So for this given maze, the minimum number of steps to reach the nearest exit is 2. So this is how our BFS approach works, where it moves level by level, considering reaching each and every cell in all the 4 directions, reducing our time complexity. So for this approach, the time complexity here would be O of m cross n, that is the size of our maze. As we visit each and every cell once at most, whereas coming to the space complexity, our space complexity will also be m cross n for the queue in worst case. So in worst case, we will push all the index values inside our queue. For example, if we have all the open spaces and 0 walls, in that case, we'll push all the cells inside our queue. So the queue in the worst case will store all the possible field values inside our maze. So the space complexity in worst case would be O of m cross n. That was our optimal approach, that by using BFS approach. So let's quickly code this approach and let's submit. So here's the code for our optimal approach. Here I've grabbed the row size and column size. I've also taken a queue of pair of int, which means it stores the index values, both row and column. So our first step here would be to push the entrance coordinates, that is entrance of 0 and entrance of 1, and we'll mark the current entrance cell as visited. We'll take number of steps, which would be initially 0. We'll also take direction vectors, and we'll start processing for each and every coordinate in our queue. So while queue becomes empty, we'll first grab the size of our queue. We'll increment our steps values since we have started processing for the entrance coordinate. And while this size becomes 0, we'll grab the current coordinates x and y, and for all the 4 directions, we'll calculate our new x and new y coordinates, and we'll first check whether this given coordinate is inside our bound of our maze or not, and also if the current new coordinate is an open space or not. So if it is a wall, we'll skip this step and we'll again move to the next direction. So since it is an open space, we'll get inside our if loop. So before pushing or marking it as visited, we'll first check whether given neighbor cell is an exit or not with the help of this given if condition, that is if it is either in the first row or first column or last row or last column, which is nx is 0 or nx is m minus 1, or ny is 0 or ny is n minus 1. So if it is an exit, we'll return step and we'll stop our loop, and if it is not, we'll mark it as visited by assigning it as plus character, and we'll push that particular current new cell inside our queue for further processing. So in this way, for each and every size of our queue, we'll traverse all the neighbors in all the 4 directions and we'll check whether we have reached an exit or not. So the moment we reach an exit, we can say that this is the shortest path, and we'll directly return the number of steps. And if we haven't reached any exit, so we'll return -1 after all this queue processing. So the time complexity of this approach is O of m cross n, and space complexity of this approach is also O of m cross n, which is far more better than the DFS approach, which took O of 4 cross m cross n. So let's quickly run this code. It's working, so let's submit. As you can see, this approach gives a successful submission. This problem is a classic BFS use case. So whenever a shortest path is involved in a problem statement, we should think BFS first. So that would be the final note of this given problem statement. So let's go to time and space complexity analysis. For our brute force approach, we have used DFS function, which generally explored all the possible paths in all the 4 possible directions. So the time complexity was 4 cross m cross n. whereas the space complexity was m cross n. And we have optimized this time complexity by using BFS approach, which generally explores in level order wise. So we have reduced the time complexity from 4 cross m cross n to m cross n, whereas space complexity remains same as we are using queue data structure to store all the possible index values. And in the worst case, if all the cells inside our maze is an open space, we'll be inserting all the cell coordinates inside our queue, which would be O of m cross n. So that's it for day 47. And if this breakdown helped you understand this problem statement, please consider giving it a like, comment, and share with your friends. And also subscribe. Also hit that bell icon so you never miss an update. So thanks for watching, and I'll see you on the next one.